The following program is brought to you by Caltech.
Good evening and welcome to tonight's Watson Lecture. My name is Ken Farley. I'm the chairman of the Division of Geological and Planetary Sciences. And I will, in just a minute, I will introduce tonight's speaker. And before I do that, I want to tell you what we have in store for the next Watson Lecture. And that is by Jonas Peters, who's the Bren Professor of Chemistry, and he's going to talk about making molecules. But tonight, it's my pleasure to introduce Professor John Eiler. John is an isotope geochemist, and he's going to tell you what that is. But at this point, I'll say that isotope geochemistry has been a signature strength of the geological and planetary sciences here at Caltech, going back many decades. And John very much lives in this tradition. He has some really remarkable results. I could tell you about awards that John has won. I think I won't do that because I know John very well. John and I actually started at Caltech at almost exactly the same time, which is more than 15 years ago. And so we've spent a lot of the development stages of our careers together. And I think one of the most fortunate things that happened to me is that early on, we co-located our labs. So we actually share a lab space. And so I've gotten to watch John develop, and one of the remarkable things about John is he thinks a lot of crazy things to try, tells you why they might be interesting, and then he goes and tests them. And what he's going to talk about tonight is the results of some of these crazy ideas. And I'm a little bit sheepish to admit that the work that he's going to talk about tonight, when he first told me he was going to do it, I remember very clearly making some very negative comment about it, saying that will never work. And it has worked. And what you're going to hear about tonight, I think, is the best kind of science. It's the kind of science that, on the one hand, answers a question. So he's going to answer a few questions that are kind of classic questions that one asks in earth science. But they also lay out an enormous new field. And there is a tremendous amount of opportunity. And I think this is the first public presentation of this work, and this is the kind of work that we are going to hear about in the decades to come. I think this is probably, well, without doubt, this is the most important advance in isotope geochemistry in the last 15 years, and maybe more. So you're going to hear about something that is really very important, and I hope you enjoy the lecture. So, John Eiler.
Thanks, Ken, for your kind introduction, and the Watson organizing staff for setting up this nice lecture, and of course all of you for coming out. If you weren't here, it would just be me saying confusing things to an empty room, so it's good that you're all here. As Ken suggested, I'm going to talk tonight about a difficult problem, about probing the events, the materials, the living creatures from deep in the geological past using some obscure, little-known physical and chemical properties of isotopes. This is a rich subject. There are many different sides to it. On one hand, it's a kind of natural science that asks very deep questions about the nature of the Earth, the way it has been in the past, the creatures that have lived on it. It's also a question with many complicated technical sides to it. What are isotopes? How do they behave? How can you observe them? How do people manipulate them? That last question leads to important societal questions. People manipulate isotopes all the time, and if you read the newspaper, you know it's a complicated issue, and we'll touch on some of that. We'll learn a little bit of the physics and chemistry behind that problem. So let's begin. Let's start working our way through this subject. I'd like to start with this quotation from Sigmund Freud, who a century ago looked at the tremendous advances in the natural sciences, and he noted two signature discoveries that changed the way people think about the Earth, their role in it, the universe. He had his own take on it, of course, being who he was. But he's correct that there were the discovery that the universe is vast and the Earth is about a tiny fragment of it, the fact that human beings are derived from the animal kingdom with its own tremendous depth of history. These are remarkable realizations that have shaped the way we think about the world. If he had lived another 50 years, he would have seen a third equally important transformation in our understanding of natural history. The background to this quotation is a landscape in southern Greenland that's composed of sedimentary rocks. They were muds and sands and silts laid down in an ocean basin 3.9 or 4 billion years ago. That the Earth is filled with materials very much like the things that we see on the surface around us, but of unimaginable antiquity. And this realization, recognized here by Stephen Jay Gould, a prominent evolutionary biologist and popularizer of thought about deep geological time, he adds this appropriately as a third tremendous discovery, that we sit not just in a vast space, not just in relation to the animal kingdom, but at a moment in time that is at the end of tremendous length of history. And so there are many different responses you can have to this. The scientific response is, great, I now have a world to explore, to discover, to unravel that is analogous to the 19th century explorers in Egypt uncovering tombs and sarcophagi. They are peering into a past that they couldn't have imagined even existed. So what we'd like to do is explore that past. And I'd like to focus the discussion by looking at two really dramatic events that shaped the way that animal life on the Earth has evolved. They're mass extinctions, periods of time when large fractions of the animal kingdom die for reasons that aren't entirely clear. This is a plot of the extinction rate in percentage of animal genera that die off in a window of perhaps a few million years versus time for the last 500 million years of Earth history. There's a background rate of sort of 10%, okay? Look around you to the left and the right. Maybe we all have, maybe that's our chance or something like that, okay? But superimposed on that are 5 recognized moments in geological time when this rate spiked, and it was not a great time to be an animal. Okay, there are a few early on, but the record is partial, and we don't talk about them much. The most recent of them is the Cretaceous-Tertiary, or KT boundary, when a gigantic bolide hit northern Mexico, and the dinosaurs all died. The first of them is the end Ordovician extinction, when a whole group of organisms that had been the dominant life forms in the Earth's oceans disappeared. Many of them disappeared. And so it was a transformation of what the animal kingdom was really like. What I'd like to do is focus on those two as examples of moments in Earth history when we can learn things about the environment. What was changing? Why did this happen? Who were the organisms that lived at this time, and what were they like? So the second question has its own unique interest. Dinosaurs, everyone knows what dinosaurs are. They were monsters that ruled the Earth 100 million years ago, and they are intrinsically interesting. We would like to know how they lived. What were they like? If you could hold one still and put your hand on its flank, what would it be like? And there is you can simplify this into a sort of Manichaean dilemma. Were they like reptiles, cold-blooded, stupid, awkward, okay, like so? Or were they like modern birds, agile, smart-ish, okay, smart enough to eat Jeff Goldblum anyway, okay? This is a question that we'd like to be able to explore, but of course, how could we distinguish them, warm from cold? I guess we could put our hands on their sides if they were alive, but we can't do that. And is there anything about their remains that will tell us what they were like metabolically, physiologically? And in particular, is there anything like this that could be observed in a 100-million-year-old fossil? So these are the two questions that are going to motivate our exploration of isotope chemistry in natural materials. In order to make much progress, we have to establish a kind of common language. And luckily, I suspect everybody here went to middle school and learned what atoms were. And so this will be a refresher course about the major constituents of atoms. So the main mass of an atom sits in the nucleus as a collection of these apparently little green and blue grapes. So they come in, these grapes come in two varieties: protons, which have significant mass. Okay, they're physical objects that weigh something, that you could pick them up with a pair of tweezers if you could find one small enough. And they are positively charged. They are electrically charged objects. Neutrons are also heavy, but not electrically charged, and so they don't participate in electrical repulsion and attraction. And then surrounding these in a sort of organized dance of orbitals are a number of electrons that are negatively charged and very low in their mass. And a really critical dynamic to the way atoms work is the attraction between the positive charge of the nucleus and the negative charge of the electrons, such that atoms, when they're stable, when they're happy, when they're in a chemically stable state, they will have a collection of electrons that more or less balances the number of protons in their core. Okay? And so we have a belief system, I would say, because we'll see in a moment that it's violated, that chemical properties of atoms mostly reflect electronic structure, the interaction of this cloud of electron orbitals of one atom with another, that electronic structure is dependent upon the existence of the positive charge in the nucleus. And therefore, what you really want to know to understand the chemistry of an atom is how many protons does it have, and what are its electrons doing? If only it were that simple. So when you start to probe the true behavior of atoms and molecules, bonded atoms, you discover all kinds of peculiar things about them. And we're going to spend a few moments now exploring what those peculiarities are, and from that exploration will come tools that will allow us to probe the past of the fossil remains that we've just discussed. So my favorite quotation to think of when talking about this subject is this one from Richard Feynman, who noted that atomic behavior is so weird, even he doesn't understand it. And if he doesn't understand it, we can't be expected to understand it, but we can certainly try. Okay, so a first important thing to note is that the periodic table of elements is a kind of lie. It is a simplification that helps us organize our thinking about the chemistry of the elements. Okay, this is the table that was on the wall of your chemistry lecture hall in high school, and hopefully you knew to look up at it during tests and so forth. And what it posits is that a location in this diagram reflects the chemical reactivity of an element. That reactivity reflects the structure of electrons around that element, and that structure of electrons reflects the number of protons in it. Here, let's look at an example. A hydrogen atom, 99.99% of natural hydrogen is a pretty simple story. It has a mass of 1 atomic unit because it has 1 proton at its center. It has 1 electron going around it because 1 proton likes to hang out with 1 electron. But hidden underneath the layer of the periodic table that you see is another world. There are isotopes. So isotopes is a Greek phrase that means at the same place, meaning at the same place in the periodic table are multiple other things that are living. So one of them is deuterium. It's hydrogen. It looks like hydrogen. It smells sort of like hydrogen. And it has a proton and electron. So chemically, it's similar to hydrogen, but it has an extra neutron in the middle. There isn't much of it. It doesn't do very much that's exciting. It's stable with respect to radioactive decay, but it exists. And its special properties will become important to us in a moment. Another is tritium. There's only about 50 kilograms of this in the entire world. It is a hydrogen atom with 2 extra neutrons. And not only is it heavy, it's also radioactive because a nucleus that's composed of a proton and 2 neutrons is unstable, and so it undergoes spontaneous decay. So the properties of isotopes violate some simple things that we all learn and hopefully internalize about chemistry and at the role of atoms in chemistry early in our education. That is Dalton's theory, which I'm sure you've all been exposed to. One of them is that reactions, chemistry, separates atoms, moves them around. Chemistry is a sort of dance of atoms trading partners in various arrangements, but it does not create or destroy atoms. There is no alchemy. We're taught alchemy is magic. Well, radioactivity is alchemy. It is the transformation of one atom into another through spontaneous activity, or it can be induced by human activity. A simple example is the decay of carbon-14, a rare radioactive isotope of carbon that's generated in the atmosphere, to make nitrogen-14, a common isotope of nitrogen, releasing energy in an electron. This happens at a steady rate that reflects the intrinsic instability of carbon-14, and because it happens at a steady rate, you can imagine using it as a clock. And so this decay scheme is the basis of measurements of the ages of carbon-bearing things, carbon-14 dating. There are many reactions like this, many ways of measuring age based upon radioactivity. We could easily spend an hour or more talking just about that. We're going to set that aside because there's another more subtle property of isotopes that will end up being more useful to us in making quantitative statements about the nature of the Earth's past, not just when, but what and who and where and so forth. That is this one. Okay, so elements are composed of indivisible particles, atoms, having identical shape, size, mass, and physical chemistry. This is an idea that atoms are the opposite of snowflakes. You're told that snowflakes are all unique. If you look at them up close, they're all special in their own way. Atoms are like, my idea at least, of ants. They're all the same, okay? They all crawl around the same way, they all look the same, they all eat the same stuff. That atoms are all the same if they're members of the same element. This is demonstrably not true. If I make water that has deuterium, the heavy isotope of hydrogen, instead of H, it boils at 101.4 degrees, not 100 degrees. It's a subtle point. You might say, yeah, 101, 100, it's all sort of the same. You'll notice the difference if you drink it, okay? It will interfere with the hydrogen bonding chemistry of proteins in your body. They will not fold correctly. They'll sort of denature like an egg, proteins in an egg, and you will fall over dead, okay? So there are important influences of hydrogen isotope substitution and other isotope substitutions on chemistry. So how can we explore this? How can we manipulate isotopes, see the forces that influence their separation, the way that they interact with the environment? There's a very simple experiment that was the starting point of our understanding of this question. It basically involves a device that's like an old-fashioned television set. I don't know how many of you remember when television sets were the size of smart cars, but they used to be gigantic evacuated boxes that had filaments in them that had electricity and generated electrons, okay? So imagine an evacuated bulb, and at one side I put a fluorescent screen that will glow when something charged strikes it, and then I heat up a piece of metal until it emits electrons. Electrons, because they're negatively charged, they're attractive to positively charged metal plates, repelled from negatively charged metal plates, and so I can steer them. I can direct where they will strike on a screen. And this is the basis of illumination of a phosphorus screen, like an old-fashioned TV. I can take exactly that device. In fact, I'm contemplating having some students do this with an old television set or something like it. Take exactly the same device, put a little gas molecule into it, right there, allow it to flow into a controlled volume where electrons will stream across it. They will knock electrons off of that atom, converting it into a positive ion. Now it has positive charge because it's lost its shroud of electrons that were balancing the protons. Now send it through this device, and it too will be deflected, attracted towards the negative charge on this plate, repelled from this one, steered to this position. One more change, and I have a really important device, a mass spectrometer. Important for me, important for history, important in a lot of different ways. What I've done is I've removed the charged plates that were applying forces to the charged particles and replaced it with a magnet, which is also capable of applying a force to a moving charged particle. Now I'm going to put not just one atom, but two, a light isotope and a heavy isotope of a gas, say, into this chamber. I'll allow them, through the wonders of PowerPoint animation, to advance into this chamber, and then I'll allow electrons to stream through them, turning them into positive ions. Now I'll send them both sequentially through this magnetic field and allow it to apply a force to them. but the force will act on two objects that differ in their mass. It'll be like pushing equally hard on a tennis ball and a bowling ball. Assuming you do it right, the tennis ball will go further, right? So my light isotope gets strongly deflected, my heavy isotope gets weakly deflected, and they end up at spatially different places. I have separated isotopes through using basically a television set. So if I make my television set big enough and dangerous enough and weird enough, I can separate isotopes of all kinds of things. This technology is used for the separation of medicinal isotopes. So if you go in for a radioisotope test or experiment at a hospital, you may well get injected into you something separated by this kind of technology. It's also the basis of uranium isotope separation during the Manhattan Project with this unbelievable device. Here is a pot the size of a bowling ball of uranium, boiling uranium metal. They send it through an amp current to ionize it and then pass it through a magnet, physically separating the flying ion beams with the very radioactive isotope landing in a little bucket that somebody then has to collect and scrape to recover the isotopes. So these things, each one is about the size of, I don't know, a large cabinet in like a dresser drawer, and they arrange them in big rings called racetracks with maybe 100 of them each. These required so much wiring, there wasn't enough copper available in the country to wire them all completely on short notice, so they spun wires out of silver from Fort Knox in order to wire these things and then melted it back down and sent it home. So this sort of technology is, in addition to making medical isotopes, making nuclear reactors and bombs, it also is the technology behind sensitive, precise isotope ratio measurements of natural things. If I can direct my ion beam through a magnet, separating isotopes into two pieces, I don't have to just fire it at a phosphorescent screen or a metal plate. I can fire it at an electronic device that is able to very sensitively measure the relative abundances of the isotopic species. And this is really at the guts of the analytical measurements that we're able to make. Let's talk about a few other processes, natural processes and human-controlled processes that separate isotopes other than through electricity or magnetics. So imagine that we have two isotopes, something heavy, something light, and they're exposed to a tube, okay, a narrow capillary, and they're moving under their own thermal motion, but one of them is light and at a given temperature is moving very quickly. The other one, because it's massive, is moving more slowly when it has the same amount of thermal energy into it. And when they race, they separate from each other. This is the basis of isotopic discrimination, one of the causes of isotopic discrimination in photosynthesis. Leaves are scrubbers for carbon dioxide, and the heavy isotopes of carbon are discriminated against when they must diffuse through the small pores that allow the gas into the reactive sites in the interior of the leaf. Here's another example. This is a photograph of fern, which is basically partly crystallized, compacted snow on the top of a glacier. And the small pores in it permit gas to become stagnant in a column. And imagine that that gas in a column has heavy isotopes at the top and light isotopes at the bottom. Common sense will tell you this is unstable. It's like a book on a table that's standing on end. The smallest nudge will make it flop over. If you're standing on a table, unless you're careful, you'll eventually end up lying on the ground in a more stable gravitational state. Okay? And the gas molecules will also sort themselves this way so that the heavy isotopes are at the bottom and the light isotopes are preferentially at the top. This is the basis of half the things you read about in the newspaper in the last year. This is the basis of a gas centrifuge, which is the main technology for isotope separation that has led nuclear proliferation in the last 30 years. The way it works is you have a cylinder which rotates fantastically quickly, generating a centripetal acceleration that's like a false gravity that reaches hundreds of thousands of times the gravitational acceleration at the Earth's surface, very strongly separating heavy isotopes from light. And the important thing about it is, instead of having gigantic warehouses filled with horrifying magnets, you have a little tiny room filled with cylinders, and it's very easy to maintain and to run. And this is why it's been so important to nuclear proliferation. Okay, so we've talked about electronic ways of separating isotopes, about simple physical ways of separating isotopes. Now let's talk about chemical ways of separating isotopes. How might chemistry separate them? So a first useful insight is to recognize that chemically bound atoms are not stationary. They are in motion with respect to each other. They're almost like a collection of masses that are joined by springs and are just oscillating and wobbling in space. But that wobbling, it's not really the way that springs operate in your normal macroscopic world. If they were, then chemical bonds would, the energy in them would depend upon how far you pulled them. If you want to put a lot of energy in a slinky, pull it all the way across the room. If you want to put a small amount of energy in, pull it just a little. And so and also, when I oscillate a slinky, unless I keep pushing on it, it will slowly dissipate energy and come to rest. If chemical bonds were like that, then when I put a small amount of energy in one chemical bond and a large amount in another, the first would oscillate a small amount and come to rest. The second would oscillate strongly and come to rest. That isn't what chemicals do. That isn't what chemical bonds actually do when you study them closely. Their energy content depends upon how fast they vibrate. It's a very different kind of mechanical behavior. They can only take on specific values for reasons having to do with the quantum mechanics of energies at this scale, and you can't do anything, at least I doubt any of us here could figure out a way to do anything, to make them stop. They're like a bell that will not stop ringing. Constant vibration at any temperature, no matter what you do, they won't stop. And so the things that have low energy contents are vibrating slowly. The things that have high energy contents are vibrating quickly. So now we know enough that we can make some statement about what isotopes have to do with all of this. Imagine I have two molecules. I've just picked hydrogen chloride, HCl acid, as an example. One of them has a hydrogen. The other has the heavy rare isotope of hydrogen, deuterium. They are oscillating, vibrating, but the presence of a heavy mass slows the vibration. And because the vibration is slowed, the energy content of this molecule is lower. And because its energy content is lower, it is more stable. Every molecule in nature would love nothing more than to have heavy isotopes in it to slow its vibrations, stabilize it, make it harder to react. Let's turn now to a kind of chemistry where we might be able to apply these principles. And it's a chemistry that's tremendously important in the geological record, both as a way of creating rocks at the Earth's surface and as a way of modulating and processing carbon dioxide in the Earth's environment to change climate state. It's carbonate chemistry. So carbon dioxide, if you breathe out, you'll have carbon dioxide in the room. If that is exposed to water, it will hydrate and make a carbonate ion. This carbonate ion can combine with metals to make all forms of familiar geological materials: shelly fossils, cave deposits, crusts in soils. Well, if you've ever been to Mono Lake, tufas, which are carbonate accumulations in mixing zones and lakes, even components of teeth and bone. Your teeth and bone are phosphate, but they have a small component of carbonate in them. It's widely distributed everywhere in nature, and it grows in environments where carbon dioxide and water are in contact, which is many environments in the Earth. So now let's imagine how isotopes might fit into this. Let's say I have a carbonate ion ready to be precipitated in a mineral and a water molecule, and they are at some certain initial energy. And they are doing their vibration thing. They're vibrating away, minding their business. And I come along with a heavy isotope of, say, oxygen, and I substitute it into the water, lowering the frequency of vibration in the water, making it more stable. This is better for everybody. Everybody involved in this system is glad that this has happened. But let's do it this way. Let's instead put the heavy isotope of oxygen in the carbonate. The carbonate has a different kind of bond from water. It's stiffer. It's like a stiffer spring. And when we do the substitution, we get an even bigger drop in energy of the system. This is even better than putting it in the water. There is a preference. All of the bonds want heavy isotopes, but they compete with each other, and the ones with the strongest, stiffest bonds win the competition and scrub the isotopes into their structures. This idea is formulated into an isotope exchange reaction here, where I have an isotopically normal, say, shelly carbonate mineral, seeing an isotopically heavy water. I might imagine them trading oxygen and making an isotopically heavy shell and an isotopically normal water. And the principles that I just described to you lead to us to expect this reaction will be driven to the right, that it's energetically favorable to go that way. Counterbalancing this is a tendency in nature for systems to become more random the hotter they get. And so I would expect that at low temperature, this reaction will be driven strongly this way, and at high temperature, less so. It will be modulated by the tendency of systems to become more randomly scattered. This is the basis of an amazingly important tool in the earth sciences that was imagined by Harold Urey, who's a Nobel Prize-winning chemist, spent his career in several places, but when he was doing this sort of work, he was at the University of Chicago, and he had working under his wings Sam Epstein, a young research scientist originally from the Canadian version of the Manhattan Project, who had come down to Chicago to learn isotope chemistry from Harold Urey. Together, they cooked up a tool for measuring temperatures in the geological past by comparing the O18 content, a rare isotope of oxygen, in carbonate versus O18 in water, a way of reconstructing temperature in the past by looking at isotopic distributions. So this has been successful on many different levels. In the geologically recent past, say the last million years or so, it has a simple application to ocean sediments. If I recover small shelly fossils of planktonic, that is floating animals that live in the oceans, and look at their oxygen 18 content, I know how to compare them to the O18 content of the oceans, and I can derive a temperature. And from this measurement, I see the rhythmic variation in climate the Earth has experienced between ice ages, when ice sheets covered most of the northern hemisphere, and interglacial periods like today, when those ice sheets retreated and occupied just Antarctica and a few small pockets in the northern hemisphere. But there's a problem. So you would imagine, great, take this tool, apply it to the deep past, and solve the problems that initially motivated us tonight. When you do this, lots of people have tried, when you do this, it's kind of a disaster. What you observe is the temperatures you reconstruct start out in the geologically recent past looking more or less like today. The further back in time you go, the hotter it seems to get and the more varied and scattered it becomes. You go back 500 million years, and the Earth apparently is like a hot tub, okay? Take a clam, put it in your hot tub, and tell me how it does. Probably not very well. Go back 3 billion years, and the Earth is boiling. Maybe, I don't know, I wasn't around, but it sounds implausible. We see lots of geological materials that remind us of sedimentary materials formed at the Earth's surface today. It seems implausible the Earth was like this. Some people have argued this is real, that this is the true variation in surface temperature. Other people have said the rocks are all compromised by post-formational processes. The second thing listed here, this is one worth exploring. Maybe it's changes in the O18 content of the ocean. Okay? Our thermometer only works if we know how much O18, the rare isotope of oxygen, is in the carbonate, how much is in water. But the ocean's a complicated place over long time scales. There are processes of hydrothermal circulation which exchange the isotopes with rocks at the surface. There are processes of weathering, formation of clay from crystalline rock, which act as a sort of sink to suck O18 out of the oceans and into the land. There are processes of glaciation, okay, now something related to climate, we'll come back to this in a moment, that will take O16 out of precipitation and store it on land. I can force the O18 content of the ocean up and down. And if I don't control for this, if I don't have some way of reconstructing it, my tool to reconstruct temperature will not work. This problem is even worse if we want to solve the problem of the body temperatures of the dinosaurs. Who knows what they were drinking or eating or where their water came from? There's all sorts of possibilities. I'm not going to be able to apply this tool in this context. And so what we've done is turn to a different approach, a different way of thinking about where isotopes are in natural materials. Instead of thinking about the competition between, say, a carbonate mineral and water for rare isotopes, this tug of war to put them in the place where the energy will be lowest, let's think about all the different forms, all the different ways in which isotopes could be present in this molecule. There's a tremendous number of them. I'm lazy by nature, and so I only put, I don't know, half a dozen or so here. There's actually something like 30 naturally occurring versions of this molecule. Here's one with an O18. Here's one with 3 O18s. Here's one with a C13. Here's one that has an O18 and a C13. And I could go on and on and on. There's tremendous diversity, richness in the isotopic content of natural things. And every single thing I've drawn on here, plus all the others you're supposed to imagine are below the screen, are unique. They're all unique in some way. They diffuse in a unique speed. They react in a unique way. They all contain their own information, their own story to tell us things. We can use this information in a variety of ways. The way that's most important for our story tonight is a kind of reaction that's similar to the competition we discussed between carbonate and water for isotopes, a kind of tug of war, but it's between coexisting molecules of the same chemical. Imagine I have in one pocket two molecules of molecular hydrogen. And they're like this. One molecule has a deuterium and a hydrogen, and so does the other. In my other pocket, I've got exactly the same isotopic content. 2 deuteriums, 2 hydrogens, exactly the same chemistry. 2 molecular hydrogen molecules, but a different arrangement. Here the deuteriums are together, here they are separated. This is the slowest vibrating, most stable bond this material can make. And so this condition is favored at low temperatures. If I heat it up enough, they'll want to be randomized. They'll want to jump into this state that's scrambled. But if it's cold, they'll want to be in this state. We can apply exactly the same principle to the carbonate species that are such an abundant part of the geological and biological record. We can imagine a reaction where a carbonate with a C13 and one with an O18 are neighbors. And at high temperature, they might be perfectly happy to stay this way. But if they get cold, they'll want to make one of these little clumps where the heavy isotopes are stuck together, the vibration rate is fantastically low, and they're very stable. And so this then is the basis for a thermometer that sounds a lot like the thermometer I told you about. It's isotopes, it's vibrations, and so forth. This one is different. All of the constituents that are bound up in a temperature-dependent reaction are in the fossil. I don't need to go back in time and sample the ocean or learn what puddle a dinosaur drank out of or anything like that. Everything I need is in my geological specimen, my shell or my bone. So the way that we actually apply this tool is we recover minerals. They might be enamel from a dinosaur's tooth or a shell or some other fossil remains. We bring that mineral into the laboratory and react it with acid to release gaseous carbon dioxide. This is put into one of these crazy devices that's like a giant television set, but with a magnet, and separate the isotopic versions with a magnet, and then measure them for a long time, as sensitively as we possibly can, to observe the relative abundances of these clumps, these 13 C18O bonds. The more there are, the colder the material was. The technical details of exactly how you calibrate this are not terribly interesting. Let's move on to the way that we actually apply it. Let's start by going back to our mass extinction problem and go to the beginning one, to this earliest one at the end of the Ordovician. And the question we'd like to ask is why? Why did they all have to die, okay? We have all of these fantastically interesting animals, Dr. Nemo's giant squids and this crazy thing that's like a Dixie straw but with a little puff on the top and whatever. You can tell I'm not a paleontologist, right? Okay, they all died. All of them died, horribly, I'm sure. We would like to know why. What made them die? Is there something we can reconstruct from the environment that will tell us why this happened? This is what the world looked like at the time, about 450 million years ago. That's North America. For some reason, we call it something else at the time. Here's most of the other land masses on the South Pole. Here's a bit of Northern Europe. Here's a bit of Northern Eurasia. We know, as a function of time, that the marine diversity, the number of animal genera, collapsed fairly quickly, about 445 million years ago. We also know, from looking at the shapes of sedimentary rocks created at this time, especially on this Gondwana large landmass, that glaciation was active at the time. It's tempting for us to relate the two together, to imagine that a kind of cold snap killed them off, and yet we can't make that connection concretely because we don't know the ages of these glacial deposits well. We don't know what was happening exactly when everybody living near the tropics croaked. Applying our method, to fossil remains, some of which are in a sort of ghostly image behind this, we're able to reconstruct quantitatively, at the level of a degree or so, the temperature of the ocean water that these fossil animals were living in. What we find is something really intriguing. First of all, the background temperature as a function of age was sort of 36 degrees centigrade. If you're really chilly this evening, that's probably the temperature of your hands or the tip of your nose or something like that. It's close to body temperature. It's actually quite a bit warmer than the modern tropical oceans. If you took modern tropical fish, go home to your tropical fish tank, turn it up to 36 degrees and call me in the morning and tell me how they did. Probably they didn't do very well. Right at the time of the mass extinction, and yet somehow the versions of these animals didn't mind being a few degrees warmer than it is today, the temperature crashed to about the temperature of the modern tropics right at the time of the demise of the Great Ordovician mass extinction. That's truly not a coincidence. It's an interesting observation. It's hard to believe they all died because of that, okay? It's just a few degrees, and it's in a direction that most things that can tolerate warm temperature, you wouldn't think they would die. I guess it's imaginable. Let's take our analysis further, though. We're going to take the temperatures that we now know, and we will return to this confounding problem of the ocean's O18 value, and like jujitsu, we will turn that problem around to our advantage. Here is the calibration of the old version of the thermometry that compares the O18 in carbonate and water to temperature. Now we know temperature. We just measured temperature using the clumping of isotopes in the carbonate. Therefore, we can use the calibration of this previous thermometer to tell us what the ratio of the isotopes in carbonate to water was like. We have carbonate in our lab, so we can just measure this. Therefore, we can solve uniquely for how much O18 was in the oceans. We can turn the problem around and try and deconvolve what was happening to the oceans during this time. When the oceans are poor in O18, it means that there's relatively little ice. We haven't stored large amounts of O16 on land. If we grow the ice sheets in glaciation, we have distilled O16 out of the oceans and left the ocean rich in O18. And over short time scales, this effect dominates and overwhelms the effects of weathering and other things that I mentioned. Using these sorts of principles, we can reconstruct not just the temperature of the ocean through time, but how big were ice sheets. And what we find is, just when everybody snuffed it, ice sheets sprung up in their magnitude, okay, exceeding the amount of ice on the Earth during the last ice age, almost doubling it. That is, we really drained the oceans. This is a map of North America just before that last ice age, where we've used this estimate of the amount of water that was removed and stored in ice to make a statement about how much shallow seawater there was covering North America. If you drain it, storing the water in ice, you have turned all of that into land. And it turns out that giant squids and so forth can't live on land. So perhaps a more plausible explanation as to why this event killed off these creatures is it's sort of like a marine version of deforestation in the Amazon. Restrict their ecosystem, and they have nowhere to go, except maybe the deep ocean where they don't want to go live. Okay, so let's set that aside. That's one example of a way in which we can reconstruct an ancient geological event, and let's turn to something a little more visceral, the body temperatures of the dinosaurs. So one way that we can try and resolve this issue is simply by looking at the shapes of their fossil remains and asking ourselves, what animals do they remind us of, and how did they make a living, okay? This is a very common line of reasoning, and you might see an example of it. Let's imagine we have a marine crocodile with a funny tail. I could argue it's like a crocodile today, and somehow it has a little funny tail that helps it swim, okay? So, and I might conclude from this, old crocodiles and new crocodiles, they're both big reptiles, they're both cold-blooded. That will be my conclusion. But this line of reasoning depends upon your ability to make accurate judgment calls. When you find a fossil, a bone in the geological record, you see it for what it is, you recognize it as the equivalent of something that you know about. Here's a quotation from, so people have known about dinosaur bones for thousands of years. And you might wonder, what did they think about them? Well, here's somebody, St. Augustine, who was not stupid. What he thought was that they were thigh bones of giant people, okay? Turns out he was wrong. But it gives you, it's an example of sorts of problems you can encounter. There is a modern version of this that is a dilemma to vertebrate paleontology today. If you look at sections of the thigh bones of large dinosaurs, like Tyrannosaurus rexes, they have structural features that remind us of modern mammals and birds. For example, they have pits and void spaces in them that suggest they had ample supply of blood to their bones through veins, like modern mammals and birds, unlike modern reptiles. So from that, you'd say Jeff Goldblum gets eaten. On the other hand, they're strongly layered. They're typically banded. This is a strange thing. Bones become banded when an animal is highly seasonal in its growth, that it will grow in the summer or the spring or whenever it has food, and will stop growing when it doesn't have access to food or its metabolism is slow. There are a few mammals that do this, but mostly we don't. Mostly we keep our metabolism revved at a high rate constantly. This is what keeps us warm-blooded, and our growth rate is continuous through the year. This by itself you might take as evidence that they were cold-blooded and that he's going to get away. So it's a line of argumentation that is not terribly definitive. Okay, so what else could we do? This also maybe isn't terribly definitive, but it's another line of argument, another insight. Let's measure their temperatures. Let's find out how warm they actually would be to the touch. And there are several outcomes we can imagine. One is they're like mammals and birds today. They have a stable body temperature that's regulated by their metabolism to be high and constant, whether they're big, little, live in a cold place or a warm place. Another possibility is that they're like modern reptiles, colder, closer to the environmental temperature, variable with their size, perhaps, but always cold. There's a final option that we really should consider given how gigantic dinosaurs were. It's something called gigantothermy. So imagine that you have a cold-blooded animal like a turtle from a terrarium or an iguana or something, except its body is the size of this room. Even at a low metabolic rate, it will be unable to shed the heat that's generated in its tissues, and its core body temperature will rise much higher than that same animal at a small scale. This is called gigantothermy, and since we're talking about animals that are potentially 10 to 100 tons, we should definitely keep it in mind. Maybe they were warm, but not because of the same reason we're warm, our basal metabolism, just because they were huge. So we can apply our techniques of isotopic clumping to several different kinds of materials from dinosaurs, the calcite from eggshells, or the carbonate units that are preserved in the enamel from their teeth. Before we did this to dinosaurs, dinosaur bones are precious and their teeth are precious. And so we thought, let's try it out on some things where we sort of know the answer. I guess I've never actually put my hand on a woolly mammoth, but I'll bet they're basically like fuzzy elephants. And this thing, it's kind of a pig, it's kind of a rhinoceros. I'll bet it also is warm-blooded like pigs and rhinoceroses and so forth. And then there are things like sharks and big alligators and so forth that I would expect to be cold-blooded. So we've looked at such animals in the present, in the geological past, and it appears that we can, maybe it's not perfect, but we can reliably see the difference between the endotherms, the warm-blooded animals that are capable of self-regulating their temperature, and the ectotherms that exchange heat with the environment and are slaved to environmental temperature to some degree. So here is a summary of all the things that you see when you measure the dinosaurs we've measured to date in teeth and in eggshells. And there's really a number of interesting observations. One of them is some of them definitely were warm-blooded. That if you were to walk up to a big brontosaurus, which is one of these animals, big sauropod, it would have a body temperature like a cow. So they were warm-blooded in a sense. On the other hand, animals a little bit smaller, the size of a big moose or a small rhinoceros, there were plenty of those, and they seem to have been systematically cooler, substantially cooler than any living mammal or bird. That's odd. We don't have anything like that in the extant record of mammals and birds. So overall, they're too variable, and they're often too cold, particularly this very smallest one. So I think gigantothermy is really the most plausible explanation in light of our measurements. That these animals were warm and they may have been vigorous, but it's because they were huge. It was not because of the reason we stay warm by regulating our metabolism to high rates. So where do we go from here? We've accomplished several things. We've explored a variety of complex subjects. Where does this all go? And we're poised to take this set of chemical principles and noting that we accomplished a fair amount by just being able to measure one new isotopic thing, a carbonate ion that has two rare isotopes in it. What if we turned our attention to molecules that are tremendously more complex in their structure, that have many sites where isotopes may be substituted? For example, here's a component of gasoline that you pump in your tank. It has 8 carbons and 18 hydrogens. There are 10 million unique versions of this thing, every single one of them different in some way in its chemistry. Glucose, your blood sugar, there are 30 million unique versions of this. Who is to say how they are subtly separated from each other during metabolism, through the course of your day, based on what you eat, if you have diabetes, other metabolic disorders? There may be a tremendous amount of information stored in these molecules, analogous to the information we retrieve from the carbonate ion. If we then go to even more complicated structures, this is something called hopane. It lives in the cell walls of microbial organisms. 30 carbons, 52 hydrogens. There's a septillion unique versions of them. I had to look that up in Google, septillion. So a septillion, apparently, is 10 to the 24th, and the universe has 100 septillions of stars, just to have you a point of reference as to what a septillion means. The information content in the isotopic anatomy, if you will, of these structures is similar to, or bigger than, the information content of the human genome. Imagine having that level of discrimination and specificity for all kinds of organic structures. It's a very attractive thing to go after. Problem is, the machine that I showed you a picture of where we study CO2 can't do it. So you have to analyze big molecules or big pieces of molecules, but any given piece can take on its mass in a lot of different ways. Here's a simple example, methane. I can make methane have a mass of 18 atomic mass units by giving it 2 deuteriums, okay, 2, 4, 5, 6. That thing is 12, that's carbon, so that's 18. Or I could have 3 normal hydrogens, a deuterium, and a C13. They're both 18. I can't tell 18 from 18, right? Also, I might take something with even more heavy isotopes and make a fragment of it in our television set mass spectrometer. Okay, that's 18. Or it might grab a hydrogen from its neighbor in our ion source. Those are 18. How do I tell these things apart? So the way that we've decided to do this is take your giant television set and make it more giant. Okay, inflate it. Bigger magnet, bigger everything, everything you can think of, make it bigger. And in doing this, we're able to separate by mass down to a part in 25,000. This, it turns out, is sufficient that all of these closely similar masses become discriminable. That if I have a thing I wish to analyze, an analyte, and a thing I don't want to analyze, an interference, very close to each other, and yet each ion beam is very narrow, I can steer the one I want into a collector, making this one stay outside in the cold. So this device exists now. We just had it created by a company, Thermo Fisher, that made this machine for us over the last year and delivered it to the Caltech labs recently. And we've started using it to probe both isotopic clumping and a new way of approaching isotopic ordering in materials. Imagine that I have a molecule like this with a sort of complex structure, and in the ion source I break it into pieces, and I analyze the isotopic content of each separately. Now I have enough information that I can reassemble differences in isotopic composition between parts of that original structure. So I have access to both position-specific information and the clumping information we've been talking about. So just in the last few weeks, we figured out how to do this in methanes, in ethanes, recognizing this clump of the hydrocarbon ethane. These are components of natural gas. Propane, we can see whether a carbon-13 sits at the end or sits in the middle. Oxygen, that you breathe or in the atmosphere. We can see these clumping species. Apparently, somebody's supposed to take their evening pills. Anybody here have an evening pill? That I recommend you take it now. Okay, and then finally, here's one of the more, it looks like a simple molecule, nitrous oxide. That's laughing gas. We will distribute it at the end of the lecture if you're interested. So 2 nitrogens and an oxygen on the end. The whole thing is sort of asymmetric, even though it looks simple. There's like 6 different versions of this thing that we've already figured out how to analyze. Tremendous information content and a tremendous range of problems that you could imagine trying to crack. Problems related to the things we discussed already, but looking instead of at dinosaurs, how about at the things they were eating? Plant remains. What about the metabolisms of microbial organisms who leave only chemical remnants in the geological record? What if we want to turn to the modern environment and understand the budgets of pollutants and greenhouse gases? Or look up into space. Meteorites, asteroids are full of organic matter that reflect prebiotic chemistry in the solar system. What maybe we can learn about that? What about natural gases and oils? All of us drove here tonight or rode in a bus or something like that, or many of us did. So maybe we'd like to know where that comes from. Forensics. This is something that has tremendous potential. If you have a chemical fingerprint that has a septillion dimensions to it, you can imagine being able to discriminate origins and chemical processing histories of all kinds of molecules, including applications in biomedical research and fundamental chemistry and biochemistry. So our subject's over, my hour is over. I'd like to finish by thanking all of the young people who have contributed to the research that I showed you tonight. This fellow is the one who probed the dinosaur body temperatures. This fellow is the one who led the paper on the Ordovician mass extinction. All these characters are struggling with these new measurements of large complex molecules, and these characters helped us buy our machines. So with that, I'll stop and take your questions.